A runner taking part in the 200-meter dash must run around the end of a track that has a circular arc with a radius of curvature of 50 meters. So we're going around like this. Here's the track. Here's the radius of curvature, 50 meters. The runner completes the 200-meter dash in 23.2 seconds. Runner completes the 200 meters, so the distance is 200 meters, and the time is 23.2 seconds, and runs at a constant speed throughout the race. What is the magnitude of their centripetal acceleration? So A centripetal, which is v squared over r, is the question mark, and so we also have that v is just distance divided by time. And so that is going to be 200 divided by 23.2. 200 divided by 23.2 is 8.621 meters per second. And so we can just plug that in. 8.621 squared divided by 50. So square that result divided by 50 equals 1.49 meters per second squared. Closest to C. An 1,100 kilogram car moves around a highway curve that has a radius, so this is a banked curve thing. The road is banked at an angle of 15 degrees. The radius of the curvature is 180 meters. The mass of the car is 1,100 kilograms. I'll define R to the left. We'll put Y to be up. The speed of the car is 25 meters per second. That's interesting. So it's giving the angle and it's giving the speed. What is the magnitude of the force of static friction of the road and the car? So normally the static friction is 0 if it's at this critical speed. Remember this, I've got in my equation that the V critical is equal to the square g times the radius times the tan of that banking angle. So I'm a little curious of what that is. 9.8 times 180 times the tangent of 15 degrees. 9.8 times 180 times 15 tan equals, square root of all that, 21.7. Okay, so that's the critical speed for which there will be 0 static friction. But it's going faster than that. So this means faster. So the free body diagram of the car is going to look like this. You've got the normal force pointing up and towards the r direction. Again, there's r, there's y. You've got accelerations, centripetal accelerations to the left. You've got now the static friction is going to have to keep it from slipping up the road since you're going faster. If you're going slower than the critical, then the static friction would keep you on the road by pushing up, because you'd be sliding down. If you're going too fast, then you need static friction to keep you on the road. So it's down like that. So that's a bit tricky. And then M1, mg acting down. Okay. What is the magnitude of the force of static? So you're trying to find static friction there. So I would say that F net in the r direction, this mv squared over r, is going to be n times, again, there's your theta there, there's your theta there. It'll be n sine theta, I don't know n unfortunately, plus fs cos theta. Well, and the f net, this is a bit of a difficult question. In the y direction, which is 0, since you're not accelerating up or down, is going to be n times cos theta minus fs sine theta. Don't forget there's a friction component pointing down now, minus mg. So we can solve for n here and then plug it into there and solve for static friction. So, but we've done the physics now. So I would say that n equals 1 over cos theta times all this stuff, fs times sine theta plus mg. And now I have to take this and plug it into here and then solve for static friction. So we'll go over here. I've got that mv squared over r is equal to, and I'll put sine theta over cos theta times Fs sine theta plus mg plus Fs times cos theta. And I need to solve for Fs here, what we're trying to find. Okay, so mv squared over r is equal to Fs, we'll times this in, sine squared theta over cos theta plus Fs times cos theta plus mg times tan theta. Okay, so what I'm going to have, if I gather the like terms here, I'll have Fs times, I'm actually going to bring out Fs over cos theta here, times sine squared theta plus cos squared theta, and then equals mv squared over r minus the mg tan theta. And we know that from a trig identity that equals 1. So we just get that Fs is equal to cos theta times mv squared over r minus mg tan theta. So it's cosine of 15 degrees times 1100 kilograms times the speed, 25 squared over 180 is the radius, minus 9.8 times tan of 15 degrees. Let's do 15 cos times 1100 times, open parentheses, 25 squared divided by 180 minus 9.8 times 15 tan, in parentheses, equals 899. Okay. 899 newtons. To keep it on the road, that is closest to B. An astronaut has a mass of 80 kilograms here on Earth and a weight of 780 newtons. When the same astronaut is on the International Space Station, which orbits 420 kilometers above the surface of the Earth, what are their mass and weight? So I'm going to assume here that weight means the force of gravity, so it's not going to be much different. So the mass can't be 0. Mass is always 80. It doesn't change. And the weight is not 0, so it's just d. So it is a little less. I guess we could work that out exactly, but I think all the other answers are nonsense, so let's just go with D. Which of the following is the best explanation of why it is difficult for a high-speed car to stay on the road when it is going around an unbanked turn? So remember, for an unbanked turn, I think it's entirely static friction that is providing the radial force is Fs, and that's going to have to be less than Fs max, or else it'll fly off the road. So I think that's what we're looking for. A, it requires a very large static friction force to provide the necessary inward force, pushing the car toward the center of circular motion. So that's exactly what I think. Let's look at the other ones. B, there is a very large force pushing the car outward, away from the center of circular motion. That is incorrect. That's a fictitious force called centrifugal force. C, there is a very large kinetic friction force pushing the car in a direction opposite its velocity. That's not true unless it's skidding. D, there's a very large force of air resistance pushing the car in a direction opposite its velocity. That might be true, but it has nothing to do with why it's hard to turn a corner. Or E, it requires a very large torque for the driver to turn the steering wheel. Yeah, I don't think that's correct. Okay. The giant swing at an amusement park consists of a vertical central shaft with a number of horizontal arms attached to its upper end. So this is the shaft, and this is the arm, and then this is the cable. Each arm supports a seat suspended from a cable 3.5 meters long, and the upper end of the cable is fastened to the arm at 0.2 meters from the central shaft as shown. What is the time of one revolution? Time of one revolution being the period t. So the idea here is we're going to use AR is equal to 4 pi squared r divided by t. That's the radial acceleration of this person going in this direction. And if you want to do a force diagram, well, she's got the tension acting up and to the left and the force of gravity acting down. And so this angle, 33, theta equals 33, is equal to this angle right here, sort of by the z rule. And so the sum of the forces in the y direction, if we define y to be up and r to be to the left, that's going to be t, I think, cos theta minus mg. This equals 0. That implies that the tension is equal to mg divided by cos theta. And then the sum of all the forces in the r direction is just t sine theta. And that has to be equal to mass times a sub r. So we have an equation for a sub r over here. We have an equation for t up here. We're going to plug both of those things into this equation. So for t, we've got m times g divided by cosine of theta times sine theta equals mass times 4 pi squared r divided by t. Oops, should be t squared, right? Okay, now the masses cancel, and we can try to solve for t. We can also we can do t squared, multiply both sides by t squared g, sine divided by cos, I'll just call that tan theta, it's by a trig identity that I know, equals 4 pi squared times r. So t is equal to the square root of 4 pi squared times r divided by g tan theta. So this is the other thing, is that we need the r for circular motion. So this is r right here. And so by geometry, r is going to be equal to the 2.0 meters plus, I think if that's the hypotenuse, it'll be 3.5 times sine theta. So it's 2 plus 3.5 times sine of 33 degrees. 33 sine times 3.5 equals plus 2 equals, I got 3.906 meters. So we're going to plug that in. So we've got t is the square root of 4 times pi squared times 3.906 all divided by 9.8 times the tangent of 33 degrees. So 4 times pi squared equals times 3.906 divided by 9.8 equals divided by 33 tan equals, and then take the square root of all that. I got 4.92, and that most closely matches up with D. Earth's orbit around the Sun is approximately a circular path with a radius of 150 million kilometers. All the answers are in million kilometers, so I'll just call it MILKM because that's what I'm going to give the final answer in. And I think I'm going to call this Earth Object 1. And it says that the period of Earth's orbit is 1 year. So again, I'm not going to convert to SI units, we're just going to keep it in these crazy units. If a new planet were discovered, Object 2, with an orbital period of 42 years, then the question is, what is its radius of its circular path? And for this, we're going to use equation 6.55 from the textbook, which states that T1 squared over T2 squared equals R1 cubed over R2 cubed. This is Kepler's third law. And you can solve it for R2. If you multiply both sides by R2 cubed, you get R2 cubed, And also, I guess, multiply both sides by t2 squared over times t1 squared. Cross multiply out equals t2 squared times r1 cubed. And then divide both sides by t1 squared. We'll get r2 cubed is equal to t2 squared over t1 squared times r1 cubed. The cube root of both sides, we're going to get that r2 up there is equal to r1 times the cube root of t2 squared over t1 squared. So it's going to be 150 million km times the cube root of 42 squared divided by 1 squared. So I do 150 times, I'm going to open bracket, do 42 squared inside the bracket, close bracket, and do to the power of a third, which is the same as cube root. And we get 1812.4 million kilometers. So that is closest to E.